Welcome, all of you. So we will start the session. We are waiting for some more participants, and then we will start the session. All right. Welcome, all of you. And it's Vijay Rahane, and I'm a Prime Minister Research Fellow in the IIT Delhi. And today, this is the third session on the molecular rearrangement and the reactive intermediates in the organic synthesis. And this session is particularly for the uh, interaction to discuss and solve some of the sample problems. So as you can able to complete the assignment questions. All right. So before going to discuss the problem, so if anyone have any doubts regarding the assignment question, so the floor is open for the questions. So we can discuss that first. So and then we'll move to the sample problems. So here, any questions if you have, please feel free to ask. So do you have any questions regarding assignment? The second thing is regarding the any any concept or any topic which are covered in the week 3. So if you have any question, please feel free to interrupt me in between. So we can discuss that question, and then we'll move to solve the other the sample questions. So these are the some sample question that I have taken from the previous assignment. So the first question is the major product in the following reactions. So you have given a starting material. So I just label it as a starting material SM. And if you look at the starting material, it has the hydroxy group. Further, it has the olefins, uh, 3 olefins, and all are the different type of olefins. Then you have added the KH, that is it's a salt, K positive, and the H negative. So this H negative is the strong base, and the solvent is given THF, and the 18 crown 6 is as a additive. So what are the product formed in the course of the following reaction? So this was the simple question that also the similar question that I have already discussed in the week 2. If you have seen that video, all right. So the question is we have given the KH which is hydride. So the source of hydride and H negative which is strongly basic. So it basically abstract the proton. So it abstract the proton. So most labile proton is the hydroxy proton. So it abstract the proton and forms a hydride. O negatively charged species. So this O negative is then involved in the 3,3 type sigmatropic rearrangement reaction. 3,3 sigmatropic rearrangement reaction, and this 3,3 sigmatropic rearrangement. So how this 1, 2, 3, if I just label it, so you can see this label, the 1, 2, and 3. These are the 3 parts of the one chain, and these are the 3. And basically the 3 and these 3 numbers, they forms a new bond. So this is the newly bond formed bond, and the uh, if I just enlarge the structure, so how the mechanism of this reaction goes. So if I just uh, draw how this 3 3 works. So if you look at this one, so this O negative and the carbon attached to O negative. So what happens? So this bond is attacks here. So this goes here, and this bond get cleaved, and it goes here. So in this way, this cyclic step get completed, and the bond between these three and the another three of the two part of the molecule. Right. So once this cyclized intermediate is formed, and now if you look at this structure, so this is a enolate. No, sorry, the O negative, which is olefinic. So this OH, so O negative can delocalize into the formation of this bond, and here there is negatively charged form, which then further abstract the proton, uh, and it gives the formation of where this proton come. So we in the course of reaction we have added the solvent THF and the KH base. That H, the basic this HH will be in the reaction, and definitely it will gonna abstract either from there or just from the acidic workup. Uh, so this H2 is gas form. So definitely these are goes out of the reaction, but in presence of aqueous workup, so this tautomerization takes place followed by this keto group is getting formed. So if you look at the answer in the following the options given, so in this one, so just simply you can directly go to here. This bond goes here. This bond goes here, and you get from the formation of. I will show the trick how you can directly go to the answer instead of directly solving all the steps. So this O negative, and so this bond goes here, right? So this after breaking this bond, the double bond will form at this position, and this the other remaining groups will be the same. So there is no any change in the other groups, right? And then further it goes to keto form. Position of double bond is in this way. The earlier position was the same. Uh, the remaining groups will be the same. So this is the product. So if you just choose the product, you can see this is the wrong. So you just neglect the option which are wrong. So if you look at another, here there is a change in the double bond. So it should be remain same. Here the double bond remains same. This bond is okay. So the answer is B. Correct answer is B. So if you look at here, so this double bond, no, this is the additional extra double bond comes from. That's not the correct answer. So the option B is the correct option here. So here is the detailed solution. Any doubt in this question? If you don't have a doubt, I'll just move to the next question. The next question about the singlet and the triplet carbines. So here the question is the multiplicity of singlet carbenides. So before going to this question, I will just show the structures of the singlet and the triplet carbene, and the difference between the singlet carbene and the triplet carbene. So if you look at the structure, so the singlet carbene, so these are the groups, and This is the lobe and this is antilobe. So this is the filled one. So this is singlet carbene. This is triplet carbene. Because if you look at the spin multiplicity, the total spin is so this half plus half, the total spin is equals to 1 plus and if the structure of the the structure of the singlet carbene is so the total spin for the triplet carbene is net zero because the both electrons are in the same orbital and both are the paired electron. So that's why it is a singlet. And this it has the in case of triplet both electrons are unpaired, so that's why it's a triplet carbene. So this is the triplet carbene and this one is the singlet carbene. This one is the triplet and this one is the singlet carbene. So right, so in this one if you look at the spin multiplicity, so how much is the spin multiplicity? So if you look at the singlet carbene, so this is the one. The total spin is plus half for the one electron and the minus half for the another electron. So the total spin in this case will be the 0. So that's why uh, this is singlet carbene. So if you look at here, so the net spin multiplicity of this singlet carbene, which is 0. So that's the answer here. And in case of the triplet, it will be total spin will be 2. The next question is on the based on the if you look at the very closely the reagent, so whenever you look this set of reagents, so you should it should in be in your mind. So in place of this reagent, this diiodomethane and the zinc complex. So in this case, diethyl zinc. So this will be a Simonson-Smith reaction and Simonson-Smith reaction. And in this reaction, always remember this set of reagent provide a CH2 carbene. And if you look at the structures, you can clearly see. So it has the now in this question, if I just have the simple olefin, let's say, in this case with this Simmons-Smith reaction, it will be uh, this product. So this newly added the CH2 comes from the CH2 I2 diiodomethane, right? So these are the this is the newly attached group, that's the CH2. And however, if you have the more than one type of alkene, in that case, the real question is, so where should be that carbene goes? So in this case, the carbene is works for electron rich alkene. So whichever the alkene is electron rich, the carbene goes to that olefin. So in this case, if you have the starting material, so this is the alkene 1 and this is the alkene 2. So, and if you look at the which alkene is electron rich, the alkene 2 is more electron rich, and therefore the reaction works at the center, at the electron rich center, and the final product in this case will be the one which has the uh, cyclization, the CH2 group attached at the olefin, which is electron rich. So this is the one which has the electron rich. This CH2 group is attached. So option C is correct option here. So why the this is the one only point you need to remember. So always keep in mind whenever the Siemens-Smith if you see this set of reagent, it will be a Siemens-Smith reaction, and it is gives the CH2 carbene, and this carbene generated from this diiodomethane, and which further attached to the olefin, which is more electron rich. So if you have some examples, so in which there are more than one type of centers are there, that time you need to always choose the olefin which is more electron rich. So I will just show some simple examples. So based on the same concept of the Siemens-Smith reaction, so I have these three. I will draw the three for better understanding. Right. So I have these three compounds. Better, I will draw all these reactivity in the same molecule instead of showing in the three different. I will write all the functional group. So let's say this is the one, this is the one, and here is another one, right? So in this case, you can see there is the olefin number one, olefin number two, and there are three olefin centers. So which one uh, where the this Siemens-Smith reaction works? So this is the Et2 zinc complex, diethyl zinc. So better draw the correct abbreviation. Plus there is a CH2I2 diiodomethane. So this is the diiodomethane is the source of the carbene, and what is the product here? So here you need to select where this Siemens-Smith reaction goes. So in this case, so which olefin you need to identify which olefin is the uh, more electron rich, and at that center the Siemens-Smith reaction works. So in this case, so what will be the product? So in this case, I will directly draw. So the product will be, this will be unreacted, this will be unreacted here, and in this case, the product will be this one. This will as the major product, because this olefin is tertiary olefin, and which is electron rich. So that's why the product is the one which to which this carbene attached to the electron rich olefin center. The next question is the what is hybridization of the singlet carbene, right? So as I have shown earlier, so we have the two different type of carbenes, whether it is singlet carbene or the triplet carbene. I will directly pick up the structures of the singlet and triplet carbene, so it will be easy for you to understand. So these are the structures of the carbenes, right? So this is singlet carbene, and this is triplet carbene. And in this case, what is hybridization? So if you look at the hybridization of this one, so you know, uh, uh, in this case, you can see this orbital, that is the one orbital is remain unhybridized. You can see this yes, this is how this the configuration of the carbon, right? And in this case, this is the structure of because if you look at this one, the both electron both are in the same orbital. So this is singlet carbene, and how this triplet carbene looks. So if you look at the triplet carbene, and this is the triplet carbene. So what is the hybridization here? The singlet carbene has the hybridization. So you can clearly see from this. So it has the hybridization. This is S and this is P1 and 2, sp2, right? So it has the sp2 hybridization for the singlet carbene. What about the triplet carbene? Triplet carbene has the two unpaired electron. So that goes to the px, py, pz. So in this case also you can see this is goes in the both the orbital equally. So that's why it is sp3 hybridization for the triplet carbene. So the correct option in for this particular question is what is hybridization of singlet carbene? The singlet carbene has the uh, one p orbital of vacant and it has the sp2 hybridization. Whether the triplet, if you have the same question, right? Instead of singlet, if there was triplet at that time, it will be uh, sp3. Any doubt here? So we are covering the concept of the hybridization. In this same manner only, I would like to highlight hybridization of the carbocation, carboanion, and carbon free radical. First, if you look at the carbocation, so it will be, if you look all the concept, then that will be very useful for you. Carbocation, right? So the carbocation means which has the one electron less, right? So I'll just draw the one carbocation. So this is the carbocation which has the one electron less. So it means one bond pair is absent, right? Because while how the carbocation is formed, so that you need to understand first. Let's say this is R, these are the all group, and this is the X. So X means it might be, let's say, take the example of the iodine. So and this is the bond which is going to break. So once this bond breaks, both the bond pair of electron will be carried to the iodide minus. So this will be I negative, and the we get a carbocation, right? So the bond breaking, obviously this bond involve the two electrons. Let's say one is in this manner and another one is this. Both the pair of electron is goes with the iodine, right? And now it has the two vacant, two less electron to fill the orbital. So this is the carbocation. And if you look at the hybridization of this carbocation, the hybridization for this carbocation will be, so you should tell now, because if you look at this one and these two orbital, so from this one, what do we get? sp2 hybridization, right? So this is the sp2 hybridization for the carbocation. So that's just a short form. I am writing C plus carbocation. And in the same manner, what is for what is hybridization for the carbon ion? So that is C negative. How this carbon ion form, that we need to first understand. So let's say this is the proton, uh, and which has the remaining other group. It might be either X, any groups, right? And if you add the base, let's say strong base, what happened? The base, let's say OH. The example is you just take the OH. Now, if you look at this head OH or any base, any strong base, so this O negative, it has the already both electrons, so it abstract the proton, and the both electrons involved in the bond formation will be goes to the this carbon center, Now the center form, which is now has the two extra electrons, right? Or the electron will be remain with the carbon. So the hybridization for this will be, I will just fill up the electrons. So yes has the both electron remain. It also have the all the electrons within these their orbitals, the hybrid orbital. So it has the sp3 hybridization. The carbon 9, the carbon negative has the sp3 hybridization. And in the same manner, so what is hybridization for? Carbon radical. So in the same manner, so how this carbon radical is going to form? So that's again the you need to understand first to understand the uh, hybridization. So this bond, let's say this is the labile bond, and this bond is going to break. So now if you look at the electron, so these are the two bond pair of electron. So how this carbon radical is get formed? So this carbon radical forms by bond dissociation of this symmetrical bond dissociation, right? So what does it mean? So one electron goes to this and one electron goes to this, the coupling partner, right? So let's say instead of dot, I will just draw the one electron. So this is how, and this X is with the another set of electrons, right? So now this is how the carbon radical is getting formed. Now it has the one electron less. So how it will be? It will be both the electron will be here for this one also. Now it has one vacant electron at the pz orbital, let's say. Now, but still, all these three x three p three either px, py, pz all are involved in the hybridization. So that's why it has the again sp3 hybridization, right? So carbon, if you look at this one, so why this one? Because of this already one electron is in the pz orbital also. So total three p orbitals are involved. So that's why sp3 hybridization for carbon radical. So carbon radical has sp3 hybridization. Carbon ion also has the sp3 hybridization, and the carbocation which has the sp2 hybridization. Similarly, the carbines, the singlet carbene has the sp2 hybridization, and the triplet carbene has the sp3 hybridization. So this is how the concepts of hybridization uh, for the particular all the intermediate that you need to remember. Then any doubt in this question? So if you don't have any doubt, I will just move to the next question. So this is the same question again based on the carbene, and it is given. So which intermediate is involved in the reaction given below, right? So if you look at this reaction, so it has the diazo salt. I will just draw the center. So this is the nitrogen, and it again has the nitrogen. This one, right? So this positive and this negative. Uh, this negative, they balance each other, right? So that's why we don't write the any uh, charge while representing in this way, right? So this is basic structure of this starting. Now what happens when it comes into contact with the light? So it goes this bond goes to, I will draw with the different color. This bond pair goes to here to stabilize this carbon carbocation. So now the the positive charge get forms at this position, and now this one is negative, and this one is, the carbon center become positive, right? Now, if you look at this, the positive charge already stabilized by the electron pairs involved in this formation of this bond, right? Uh, Now, if you look at this negatively charged, which has the nitrogen and nitrogen, which has negative charge. Now, this bond involved here, so it forms the triple bond, and then this bond break and with retain this carbon atom bond break and retain the electrons, the pair of electrons involved in the bond formation, and it forms intermediate. So if you look at the this intermediate, so this intermediate now initially it has the positive charge, now it has the negative charge, right? So what does it mean? Not negative charge, the two error electron. So total it has the earlier it has two electron deficient. Now it has the again two electrons. So it is overall net neutral, uh, but only with the two bond. So what how this if you just draw the hybridization wise, so these are, let's say, the hybrid states of this earlier molecule, right? So it has the all four bond coupled, and not in this way. It has the sp2 hybridization, right? Earlier. So this olefin, it has earlier sp2 hybridization. Now, if you look at when it goes to from this step A to step B, now it has the hybridization changed to, sorry, hybridization remains same, but the electrons are less, right? So it again has the sp2 hybridization, but both the electrons are has taken right. So the two electrons are already pulled from this center, but still hybridization will remain same, sp2. Now, if you look at the third stage, so that is the this was the B. Now it is C. Now what happens? The two electron involved in this bond formation will be goes to in the same orbital, or whether it is same or different. So this bond between carbon and nitrogen get eliminated. Now I will try it in the there's some different color. So this it forms a carbene with two vacant orbitals because two bonds are now unavailable, right? So this is the sp, sorry, one bond, the bond electrons get paired. So this is the two electron, it retained the two electrons from this bond. So now it is again sp, whether either it is triplet carbene or the singlet carbene, but it remain the same. So with this position of this bond, whether it might be in the both will be in the same orbital, or maybe in the two different orbital. That depends upon the nature of the carbene, whether it is singlet carbene or triplet carbene. So let's consider this as a triplet. So this is how the it is going to form, and then the the second molecule, that is the olefin. So this carbene and the olefin comes in contact. So it is same as the Siemens-Smith type reaction. It forms a cyclopropane intermediate, and so this was the starting. Now when it comes into contact with this one, so I'll just rub this to show. So now we have uh, this plus this, the carbene plus olefin. It forms, this was the part of olefin. It forms a two a bond between these two carbons, adjacent carbon of the olefins, and you'll get the product. So in this case, you can see it has involved the carbon intermediate. So that's the key. The question was the what which intermediate involved. So this carbon intermediate is involved in this one. Next question is based on the same Siemens-Smith Siemens-Smith reaction. So you have given the CH2I2 and the olefin, and here it involves the stereochemical aspects. So always keep in mind this Siemens-Smith reaction follows the CH2 group attached on the same carbon atom. So if you look at here, the starting, you have given a starting with the this pH with the methyl. So the pH is directing upward, let's say, and obviously the backside there will be hydrogen. In this case, the hydrogen is directing front side, and this CH3 group directing backside. So after the completion of reaction, the stereochemistry of this will be the remain same. So the pH will be directing front. Again, hydrogen. There will be a CH3, and there will be hydrogen backside, and this will be, let's say, in the plane. So this will be the product in the after the completion of this reaction. So if you look at obviously the option C and the D option are the incorrect options. Now the question between whether it is A or B. So if you look at this phenyl, in the starting it was anti. So in the starting product it should be anti. So the option A is the correct option here, and B is the wrong option, because if you look at the stereochemistry, so the stereochemistry is changed in they have shown change, so it is incorrect one. The next question is based on the again the nitrate intermediate, that the same question we have seen earlier. So you have given N2. So this N2 in presence of light. So each in presence of light it forms a carbene that we have already seen, and this carbene is again converted into the ketene by the formation of the pathway. So this alpha bond to the carbonyl get used, go migrate to the towards the carbene, and then this negatively charged, then after forming this bond on the carbene will involved in the double bond formation. So there was an intermediate step that they have excluded. I will just elaborate the step. Right. So this is the step going to form. This negative charge is formed at this position, and now again this involved in the bond formation. It forms a ketene. So this ketene on reaction with the water, it goes converted into the carboxylic acid. So this is the product is getting formed in this reaction. So here, if you look at the options, so obviously this is not the correct option, and this is also not the correct option. So, so this option they have given. Is there any possibility or any mechanism by which some other bond cleavage leads to the formation of such compound? We can check that one also. So let's say other group migrated. What are the possible groups? So obviously, that's the only group that can attack on the carbene, because this side already it is carbene, the side on which the carbene is there. So this is again, wrong option. Option C is the correct option here. All right. The next question further is the major product formed in the following reaction. So here we have given this into it's just the similar earlier as shown earlier, which is source of carbene. So here the question is which is the electron the always carbon always attack. So I will just draw this intermediate step. So it will be ETO OC CH. So this is the carbene getting formed. Now this carbene react on the electron rich center. So in this case you can see both are the symmetrical. So it will whether it is formed either here or here, it will be the product will be the same. So the option A is correct option here. This is obviously wrong. This is again wrong because if you look at they have the double bond was not here, and this is also again wrong. Option A is correct answer here. You can see here also, which is again the same carbene is formed and which further attacks on the let's say here, and this further COOET group will be remain same. Further, next question is based on the EPR activity. So always keep in mind, so the molecule which has one unpaired electron at least, they are uh, EPR active. Condition for EPR activity. At least one unpaired electron is must required in the molecule to show the EPR signal. So in this case, you can see this is the singlet carbene, and this one is the triplet carbene. And if you look at the structure of the singlet and the triplet carbene, so if you look at this triplet carbene which has the two unpaired electron, so obviously this will be EPR active. But if you look at the singlet carbene, singlet carbene doesn't have any unpaired electron. So only triplet carbene has the two unpaired electron, and that's why it shows the EPR signal. Singlet carbene doesn't show any EPR signal. The next question is the which of the following compound cannot give Hofmann rearrangement? So first of all, you should know what is Hofmann rearrangement, and uh, then you can uh, identify the compound. So if you look at the structures, so I will just elaborate the structure. So to show the Hofmann rearrangement reaction, you need to have the NH2, right? Because then only it will convert into the such. So in presence of base in the Hofmann rearrangement reaction, this intermediate is it forms, and further this N2 eliminate to give the such further reaction. But if you look at here, the first starting which has the NH2 group is okay. The second, if you just elaborate this one, which again has the NH2. The third one again has the NH2. So this one is okay, this one is okay, this one is okay. But if you look at this one, this has only an H. So cannot give is this cannot give, and this can give. So option B is correct option here. So this is the structure of carbon. This is the secondary carbamide. Secondary tertiary carbamide. They don't give the Hofmann rearrangement reaction. So that's why the option B is the option here. All right. So next question in this case is the based on the intermediate. So among the following reactions, which does not involve isocyanate as an intermediate. So I believe you should able to answer the question. So which intermediate? First of all, revise all the rearrangement. See the. I will just show the steps to solve the question. See mechanism, all these reaction, and then you will get to know whether this rearrangement involve isocyanate intermediate or ketene intermediate or any kind of carbene, this sort of intermediate. So see the mechanism, and then only you can able to identify. So the option here is the Wolf rearrangement, and but for your understanding, see these mechanisms of this rearrangement reaction. If you just Google it, you will get the correct answer. The next question is, which is the incorrect statement for the nitrine? The first one, nitrine are the 6 electron monovalent and uncharged species. The triplet nitrine is, we'll see one by one, which is the incorrect statement. The first one is the nitrine are the 6 electron species. It is up to here is correct. Then it is monovalent, that again correct. Uncharged species. So the net charge on the nitrine will be obviously 0, because nitrine is in the same manner we have seen the example of the carbene. So this is the carbene intermediate, and the nitrine will be same. Let's say R. So this will be the nitrine intermediate. So it is monovalent. It has only one uh, bond, uncharged species. All right, that's up to here is correct. Then the next question is, triplet nitrine is lower in energy compared to the singlet nitrine. That again correct. The triplet uh, nitrine is ESR inactive. That's the wrong one. The singlet, because obviously in the triplet we have already seen in the triplet, which obviously will have the this set of uh, configuration, which has the two unpaired electron. So obviously it should be active. ESR means electron spin resonance. The singlet triplet energy gap of the imidazole is higher than the carbene. That's again the correct option. So this is the incorrect statement, and you need to identify incorrect statement. So this is the option here. And what is wrong in this statement is the inactive. It should be active, because the triplet which has the two unpaired electron, and whether it has two unpaired electron or one unpaired electron, all these compound are the which has the unpaired electron, they are ESR active. Next question again based on the same the mechanism that we have seen earlier. So the find the major product in the following. So this is only thing is as we seen the carbon intermediate some reaction. So this is the nitrogen intermediate. So I will just elaborate the structure. So this is ethyl O, C double bond O, and here if you look at this one, this N triple bond N. So this is the N positive and this is the N negative. And when this eliminate nitrogen, it get converted into N plus N2, which is eliminated. Now this is the nitrine, and this nitrine, once this nitrine is formed, it react with the again the same electron-rich olefin and gives the product like this. I'll just add the structure of this product. So the nitrogen will be here, and this remaining double bond O ET remaining group will be the same. So this is the product gonna form. Now if you look at the structure, so this hydrogen will be on the same side, will be here same side, methyl will be on same side. The product A is the correct option here. In this case, if you look at these hydrogen positions, that's the wrong. In this case, this they have written anti. So this again they have changed the stereochemistry. The option A is the correct option here. The mechanism is similar as the carbene. Only the method to generate the carbene and nitrines are different. So that's the basic change here. So yeah, so this is the nitrine and it gives the similar reaction as like the carbene. Right. So does anyone have any doubt up to here? Right. If you don't have any doubt, then we'll move to the next question. So which is again based on the so we have seen carbene, nitrine, and some reactions. So these are the some question based on the stabilities of the radical. And I think we have seen this question earlier as well. So we have given uh, multiple, sorry, four radicals, and you need to identify which radical is stable. So if you look at here, the stability of radical. So basically, radical is electron deficient, one electron less compared to the normal usual stable molecule. And in this case, we need electron donation for the to get the stability to the radical. And so the group which gives the electron donate the electron, so that will be preferred for the stability. So in this stage structure, I will just elaborate the structure. So this is the structure. So this is structure for this molecule, right? The another molecules are this one, and this is the molecule. So if you look at this structure, so this molecule is definitely this radical is definitely not stable. So because if you look at which has the olefin directly on the carbon, which has the radical. So the first one is the least stable. So we will go to directly that we'll negate other options. So this option is wrong. Right, we directly got the correct answer here. So this is the correct answer, and we'll see one by how why I am showing the option C is correct here. The next question, next option here is the next molecule here, which has the radical on the olefin, which is adjacent. So it gives us some stability. So if this if it delocalize this double bond in the system, so it gets some sort of stability due to the mesomeric structure or the resonance structure, and this is one possible structure for the same molecule, right? because of this delocalization of this bond across this molecule, right? The next one here also has the same. So this radical involved in the bond formation here, and it gives the radical upon delocalization at this position, right? So the two mesomeric structures are formed. For this one, if you look at the stability of this one, it doesn't have resonance stabilization, but it doesn't have a negative effect like electron withdrawing. So, so this is the least stable. So this is the fourth number. This is the third, and in this case, this is the second, and this is the first. So the order should be 3 is more stable compared to the 2, which is stable compared to 4, and again compared to 1. So this is how the stability order for this. Yeah. So this is the stability order. Next question. Yeah, the same question here also. So this is the detailed answer. You can see the I will upload this PPT, so you can see the detailed answer. So the allyl radical is more stable than the tertiary radical and then the primary. The next question is resonance effect, also inductive effect that stabilize these radicals. So here we have given the next questions, and which is particularly on the similarly the stability, and for that also the same explanation goes to this one also. So this is the olefinic, so this is the least stable. So the option which has these fourth at the end, so which are valid options. All right, up to here is okay. Then if you look at this radical, the one, then if you look at why this radical, because it does only have the stability due to hyperconjugation, but options are not, other stabilization factor is not for this uh, compound 2. The compound 2, sorry, compound 1. The compound 2 has the stability due to the resonance stabilization. So in this way, it will get some sort of stability, and it will do localize in the ring. Then this is the compound 2. Sorry, but if you look at the 3, compound 3, which again has the stability due to the 3 inductive effect, and also it is a tertiary radical. So if you just neglect the other options, so 4 and 2, 4 and 2 is okay, 4 and 2 is okay, 4 and, sorry, 4 and 1, 4 and 2 is not okay, 4 and 3 is not okay. Right, among the C and the D, so which is correct option here? So that we need to identify. So in this case, the hyperconjugation and here the resonance stabilization. So which effect is dominant? The resonance effect is more dominant compared to the hyperconjugation or the inductive effect. So that you need to keep in mind. And also benzylic radical are more stable than the tertiary radical, than the primary radical, than the phenyl radical. So that's the question, and see the answer for the question. Here also the same. Here is the persistent radical. All right. So this is the question. Persistent means the radical which is the stable at the room temperature also and live longer. So this is the BST. we using the radical trapping experiment for the photochemical reaction. If you are someone doing research in the carrying out the photochemical transformation, so A plus B plus C, it gives the some sort of product, and which is influence of H nu light. That time, whether the mechanism goes through the radical pathway or that to identify mechanism, uh, to confirm radical pathway. We use this BHT because it has the stability due to this resonance stabilization also. Once this so how this stability it get, so this is how it go. It can further convert into the this form. In this case, you can see it has this radical at this position, right? And further, it again delocalization uh, to this position and again this position. So that's why it get the many more and more resonance structures are possible. And also the steric crowd is also one of the factor to get the stability. So these persistent free radicals are radicals they that have longer lifetime than the other radicals under the same condition. Also, they can be stabilized by steric crowding around the radical center. So as we seen in the next one, this is the steric crowding. Because of this steric crowding, uh, uh, it gives some stabilization. Also by delocalization of the unpaired electron into the adjacent pi electron. So these are the some persistent example. Sorry, these are the uh, this is about the persistent radical. So there are some other radicals also. So like uh, these are the some well-known examples of these stable radicals. Radical expression. This is also one example of stable radical. So this radical also is stable at room temperature also. So and also instead of this chloro, if there are some other groups like other halo, that are also again some examples of the stable radicals. All right, moving to the next question. Before moving to the next question, I would like to mention, as the professor also informed last week, so there will be some interaction section with the professor. So please take the advantage of that one also to clear your doubts, and also register for the examination is mandatory to get the certificate. The examination will be very easy. So all the question based on the assignment that the question that I am solving here in the this interaction session, or also from the assignment which are given in the portal. So based on that two different assignment, only the question will be from that one only majorly. So 60% question will be this from the assignment, and more than 80% will be from the syllabus only. So please take the advantage, register for the examination. So you will get the certificate, and also you will get a chance for 1 year internship, paid internship with the professors group. So if anyone interested, uh, so please register for examination and uh, study the course, get the higher mark. So those who get the good marks, they will have the chance to apply to a professor for the internship. The next question is again based on the peroxide effect for the across the olefin, addition of the HBr on the olefin. So this question I will leave up to you because the same question without peroxide I have already explained. So what happens without peroxide? And in this case, so in place of HBr, so what is product? And with the same, in place of HBr plus H2O2, what is the two product? What is the product? So in both the cases, the products will be different. So see that the reaction mechanisms. So you will get answers. So for that one, I will for this peroxide one, I will show the answer here. So how this peroxide is shows the homolytic cleavage and the radical. So in this case, O radical is attacks on the HBr. Further, it gives the Br radical, and this Br radical forms a bond homolytically, and it forms a stable tertiary radical. So the attack takes place in such a way that we get a stable radical. So that's the key method here. And further, this radical abstracts the proton from the HBr again, and it forms the product plus Br radical again, and the cycle will be continued. So if you have any doubt, please let me know. I will wait for 5 to 10 minutes. And if you don't have any doubt, then I will move to I will stop the session here for today. So if you have any doubt, please let me know. So if you have any doubt, so please let me know, or you can leave the meeting if you don't have any doubt. All right. If you don't have any doubt, you can solve this question. So this question, this question is based on the basically the same concept on the radical mechanism. In this NBS mechanism, what happens? So this is the question, and you generate this NBS basically the source of bromide and in the form of radical. So this the structures of NBS is this is the one structure, and in terms of light, so it shows the homolytic cleavage. This radical at the nitrogen and radical at the bromine is forms, and when this react with the olefin, so in this case the olefin is covalent and Br radical. So those Br radical forms a homolytic bond with the one. So it forms a radical, the stable one. So if it forms the bond at this position, so which radical is gonna form? All right. So this is in this case, it will not go by this mechanism. So once it forms a Br radical, so this Br radical is uh, abstract proton and it forms a HBr, and then the radical get forms, and which further again the second molecule uh, from Br radical, and the radical forms at this position with with this product. So in this case, initially I was thinking to it will react with the olefin and it forms this one, but the reaction doesn't go by the mechanism. So please check this the reactivity. So this NVS radical. So it is not the same with the that we have seen earlier. This peroxide one, HBr plus peroxide, it go use the Br radical, and this Br radical further involved in the hydrobromination on the olefin, oligophenylene, oligophen, oligophen, olefin. Sorry. So these are the some examples. So I hope your doubts. I have given some variety of examples. So you are able to solve the assignment questions. I will stop here for today, and the next session will be on the next Tuesday. Thank you.